All right. So I've posted midterm grades. I think you guys have seen it by now, and so those are on CCLE. I do have a few students who need to take makeup exams, so you are allowed to review your exam starting on Monday. Okay, so just hold off until then. But overall, the performance was about where I expected it to be. The median being an 82, and some students doing very well, some students doing not as great, but that's okay. And I just want to remind you that this is just one little test in one class that doesn't really even matter, and so it's worth 15%. So even if you did poorly, like, you can recover, and also at the end of the day, your grades are not that important. They really aren't. Okay, they don't. Your performance on an exam, your performance in a class, they don't determine your value as a person, or they're not a sign of what you're capable of or anything like that. Just your performance on an exam. So I don't want anybody's kind of self-worth or feelings about themselves be tied to their academic performance. Anyway, yeah, we'll just want to get everybody through the class, get you guys graduated, or those of you who are coming back next year, then just get this off your checklist. So okay. Any questions before I get started on today's stuff? We're doing all right? Okay. I'm going to spend a little bit of time just kind of giving some perspective, because I'm going to take a little bit of a detour, I guess, using, some instructor-given freedom regarding the content of our course, okay? So the title of our class is Monte Carlo Methods, Intro to Monte Carlo Methods. And if we stuck with a strictly Monte Carlo methods class, we would learn these Monte Carlo methods, but in my opinion, there wouldn't be a whole lot of context, okay? And I don't know, maybe you have that feeling already, or maybe not, in that so far in the first 3-4 weeks of our class, we've been spending time generating random variables, and then we just started talking about Monte Carlo integration and importance sampling. And there might be a little bit of a nagging question where you're like, what is the application of this? What am I going to do this? Where am I going to use this? And so I'm going to take a small detour to try to build up, a case for using the methods that I will be introducing. So let me just kind of do a little recap. So far in this is our class, Monte Carlo Methods. So far in Monte Carlo Methods, what we've done is random sampling from pretty much almost any variable, almost any univariate random variable, okay? And then we've done kind of Monte Carlo estimation to estimate expected values. Okay, so That's what we've done so far. And so what I want to do is what's coming up next, okay? Coming soon. Is what we call the Metropolis-Hastings algorithm. And also Gibbs sampling. Okay, and these are both Markov chain Monte Carlo, or what we might call them MCMC. And so, we'll have a talk about what a Markov chain is, and we'll discuss these algorithms. But these algorithms all by themselves, without any context, I feel like is you lose some perspective of why we bother with this. Okay. So let me kind of provide a little bit of big picture, and then we'll start getting into kind of the field where we're going to use this, okay? All right, so here's the idea. Right now, we can sample from almost any univariate random variable, all right? If we've got a PDF, we can create so we've got, for a univariate variable, all right, so I'll say right now, this is what we can do. So we've got, we'll have a PDF, and then on the computer, how do we draw a PDF? What happens is, oftentimes, to draw the PDF, because the computer doesn't understand continuous variables, right? Computer doesn't know what a continuous variable is. To draw a PDF, we often create, we do something like this. We'll do S is equal to some kind of sequence from, I don't know, we'll say 0 to 5, and we'll go by 0.001 or something like that, okay? And if we do this, how many values will be in S? We'll have, S will have length 5001, right? Okay. Or 5,000, 5,000, and so 0 to 4999 would be 5,000, and then to 5 would be 5001, okay? And effectively, we're just like, we have a whole bunch of dots that are very, very, very close together, and the computer kind of links them all together and forms, this is effectively what the computer sees, and then when we graph it, it connects the dot, and it looks like a smooth curve because, with 5,000 dots, things smooth out, right? Does this kind of make sense? All right. Now, what if we wanted to do this for a two-dimensional distribution? Okay, so what if we have, here, let me just write this. Right now, what we can do is to draw the PDF, so the computer plots, 5,001 points and connects the dots. Okay, and it looks like a smooth line. Okay. Okay. What if we have a 2D function? Okay. Then what I would have to do is I would have to create a grid for both variables. Okay. So I would have kind of a S1 will be, we'll say, a sequence from 0 to 5 by 0.001, okay? And then I'll have S2, which will be another sequence of from 0 to 5 by equal to 0.001, okay? So this will have a length of 5001. And this will also have a length of 5001, okay? And then I'm going to create kind of a grid okay, and each of these, at every combination, we would get some kind of surface plot, okay, and we would get some kind of, I don't know, this is hard to draw, but effectively, you know. So we'd have some kind of surface that goes like this, and you have this, you end up getting this rectangle-looking thing to kind of illustrate this three-dimensional surface. You've got S1 along one side, and then S2 along this side, okay? And then at the intersection of all of these points, we figure out the density, and we graph this, right? So in order to create this surface, how many points did I have to calculate? 5,001 squared, right? So on the order of 25 million. Okay, so I had to calculate 25 million points, and I find the density at all 25 million points, right? I'm doing this correctly, right? 25 million, and then plus that, and then we can plot this out, right? So I have a grid of 5001 by 5001, and this is like 25 million. All right, so that's a lot of 25 million points in calculations. Points to calculate. Okay. And what would happen if I had 3 dimensions? And I did the same kind of method here. Now I can't draw this because it's going to be in 4-dimensional space, so I can't draw it. But if we wanted to create a grid approximation of a 3-dimensional density, it would require on the order of 125 billion points. If we're doing 5,000, if we're doing about 5,000 points in each dimension, then it would require 125 billion, right? And it's just going to climb geometrically for every dimension that I add, okay? Or is it exponential? I don't know. Okay, so it climbs, so for a density of 3 dimensions, grid approximation, with 5,000 points in each dimension, will require 5,000 to the third, about 125 billion points. Okay, and the number of calculations just keeps growing, right? Keeps growing with more dimensions. Okay. And so we need to have a better method, okay? the problem is especially compounded, or yeah, so we need to come up with a better method, and we recognize that this is extremely inefficient, especially because oftentimes when we look at densities of random variables, there's only going to be like one pocket or just small areas where the values have meaning or higher density, okay? So so let me just kind of illustrate this. So let's all right, so this method, so grid approximation is inefficient. Okay, so while we can use grid approximation to draw PDFs of one variable, which is what we've been doing so far. Every time you type in s is equal to a sequence from 0 to 1 by 0.001, and then you use that and you say create the PDF of s versus, plot s versus the PDF of s, like s versus the p-norm s or whatever. Whenever you're doing that, you're doing a grid approximation because the computer doesn't understand continuous variables. It's just plotting a whole bunch of little dots and connecting them. And we go, oh, that looks like a nice smooth line, okay? That's what we've been doing so far. And so here's just like a 2D example, is oftentimes you'll have the entire kind of, this might be just like one spot of our two-dimensional density, and there's just like one little zone here, okay? So most of the time, it's just close to 0, all right? So you just got these, you have this grid where it's like pretty much all flat, except this one little zone where you have like this, something like this, okay? There's just one spot where there's a hill, okay? And so when you're calculating, so in this case, what did I say? I said there's 25 million points, okay? So for almost all of these things, it's not exactly 0, but pretty much when you say like, okay, what is the density at this location right here? It's the density here, the density of x, what variables do I want to use? Okay, so we'll say the density at x and y may be on the order of like 1 times 10 to the minus 12 or something like that, okay? Something, it's not exactly 0 because these are, I don't know, out there, okay? But it's on a practical basis, it's close to 0, okay? And you calculate, okay, what's the value at this location, right? And then you say, what's f of x, y? And again, it's close to 0. And so you're like wasting computer time trying to do like all of these points where the answer is pretty much almost 0, okay? Really, we just want to spend our time in this zone right here where like this is the only spot that's interesting. Okay? This is, we want to spend our time here. Okay? If we knew this is the interesting spot, we could just do grid approximation in this one location and we could get like a good answer. Okay? But we don't know where this is, right? Like here I'm drawing this out and I'm saying, this is where we want to spend time, but we don't know where this is. Okay, this is the problem. So we want to spend our time here, but we don't know where it is, okay? So this is where we want to draw our points, because out here it's like it's just pretty flat, okay? It's pretty close to 0. There's not a whole lot of stuff that's interesting, right? Because maybe you want to calculate the expected value over this two-dimensional surface, right? So we're doing Monte Carlo integration. So with Monte Carlo integration, we're just randomly sampling evenly across, like if we did the uniform case, but it's two-dimensional, we would just randomly sample across this entire thing. And like 95% of my values are going to be close to 0, or, depending, in even higher dimensional things, it might be like 99% of your values, or even more than that, are going to be close to 0. And so while you're doing this, your estimate of the expected value is terrible, and it's only until you get to this region of interest, which has a spike, that you get something interesting, right? It'd be kind of like so can you imagine doing Monte Carlo integration for the normal model, okay? But you're doing the uniform case, and you say, well, you know what? The normal model technically goes from negative infinity to positive infinity, but I don't want to do that, so I'm going to randomly sample from negative 1,000 to positive 1,000, okay? So you're randomly sampling from minus 1,000 and positive 1,000, and pretty much every time you sample a value uniformly on there, like almost all of those values are returning values that are close to 0, okay? And it's only if you randomly sample values between like -2 and +2 that you get something that has some kind of value to the density, okay? Maybe even -3 to +3, right? So there's only like that window of like 6 out of 1,000 where you're getting values, and you need all of this stuff to try to get the true answer to the expected value, okay? And so so that's what we've got going on, except it's just the problem's magnified in the high dimensional case. So what we have is we've got a few methods. One of them is going to be the Metropolis-Hastings algorithm and Gibbs sampling. They both kind of use some similar ideas in that let me see if I can cut this out for the next slide. Okay. Okay, so our Markov chain Monte Carlo method, Monte Carlo. Well, basically, you'll start at some point. Okay, you start here, and the Markov chain kind of moves randomly in these different paths. But what's going to happen is the Markov chain will tend to move in the direction of higher density, okay? So this surface, even though it looks flat, is not technically flat. There's just like the ever slightest slope to it, right? So like the value right here is going to be ever so slightly higher than the value over here, okay? And so these Markov chain methods tend to favor areas of higher probability, okay? So the methods favor areas of higher probability, okay? And it doesn't, but it's not strictly saying I must always increase every single time, okay? It's not like an optimization thing where it's like it must make improvements every single time. It can go backwards, but it favors moving towards regions of higher probability, okay? And so this area is technically lower than this area, even though it's very flat. There's ever so slight, a slight slope, right? You can imagine, just think of the normal distribution between what's the probability of randomly sampling a value of 20 versus randomly sampling a value of 50 from the standard normal. Both of them have probabilities very close to 0, but it's technically more probable to sample a value of 20 randomly than it is to sample a value of 50 randomly, right? And so you'll move towards these directions of higher probability. Okay, and then so that helps you find this region of interest, and you'll kind of spend most of your time in here. Okay, and you'll get and you'll keep sampling values, and once you're in here, you're going to just keep moving back and forth in this kind of zone. All sorts of like that. So the method will favor areas of higher probability. Okay, and this helps us, quote, find the region that we are interested in. Okay, and this helps us basically randomly sample the distribution. Okay, and then just like before, we generate a large random sample from the distribution to get an approximation of what the density looks like and get an approximation of its properties, like the mean and expected value, or the expected value. Okay, so so we then use the random sample to approximate density and approximate properties of the distribution. Okay. Does this kind of make sense? Okay. So this is kind of where we are headed, okay? And again, I want to give you some context and application, and one of these is going to be in Bayesian statistics, okay? And we don't have, as far as I know, the stats department doesn't currently offer a Bayesian data analysis course for undergrads, and so I'm going to take the liberty and we're going to delve into a little bit into Bayesian statistics to give our Monte Carlo method some context here, okay? And so I'm going to start off with kind of like the most basic Bayesian example, and then and we'll go in there. And I know I also covered a little bit of Bayesian statistics in 102B, so if you've taken my 102B class, then some of this stuff will look familiar. I think that's okay. It plays a role in 102B as well. So, okay. So, so I'll say important application. So let me just kind of tell you what's going to happen is we're going to start getting into Bayesian stuff, and then we will be learning Bayesian and this Markov chain stuff together, and we'll be continually building up our ability to analyze Bayesian data using these Markov chain Monte Carlo methods in that context. Okay, so important application will be Bayesian statistics, okay? So I'm going to just start with some kind of background base information on Bayesian statistics, okay? All right. So first, let's just review frequentist statistics. So this is probably what you've learned so far. Frequentist statistics, so think stats 10. And let's say you wanted to estimate the mean of a population. All right, so we want to estimate mu, the population mean. What do we use? Okay, so we want to estimate mu, the population mean, all right? And so what we use is our best guess is x bar, the sample mean. But we don't say mu is equal to the sample mean. What do we say? We create an interval. What's it called? We create a what? A confidence interval, right? And why did we call it a confidence interval? So the confidence interval is going to be x bar plus or minus t times the standard error. And the interpretation was something like, I am 95% what? Confident that mu is between, I don't know, 10 and 15, okay? Something like that, right? Well, if you took my Stats 10 class, I took great pains to say, we say confident and not probability, right? We say like, don't say there's a 95% probability that mu is between 10 and 15. We say I'm 95% confident that mu is between 10 and 15, but we can't say probability. And what's the reason for that? Yes?
The probability is 0 or 1.
Yeah, there's no probability associated with mu because mu is considered to be a fixed value. It's either in the interval or it's not, okay? So mu is considered to be a fixed value. It's like just a property of the population. Okay, so there's no probability associated with mu. With mu, it either is in the interval or it's not. Okay, does that sound familiar? Okay, yes, good, okay. Like 3 of you are nodding your head and 1 person said yes, so I guess we're good then. Okay, I'm going to close this poll here. Bayesian statistics, okay? So contrast. Okay, in Bayesian statistics, the value mu, the parameter itself is a random variable, okay? Or I'll say the parameter, the value mu itself is, is a random variable. Okay, so mu is drawn from some probability distribution. Mu is drawn from a probability distribution, okay? Frequentist classical statistics, mu is a fixed value. We don't know what it is. We use sampling distributions. We say if the null hypothesis has this mu, which is set in stone, this is what our things look like. Okay? In Bayesian statistics, we say, you know what? Mu itself is a random variable, and mu is drawn from a probability distribution. Okay? And we start off with a probability distribution expressing our prior beliefs about mu, and then we use the data to update or refine our beliefs about mu, and what we end up getting is another probability distribution that represents what we believe about mu. Okay? So mu itself, mu is drawn from probability distribution. Okay? And so in Bayesian statistics, we begin with a probability distribution to represent our beliefs about mu before or prior to seeing any data. Okay. Then we update our beliefs, we'll call that, our beliefs about mu using our data. And then we end up with another probability distribution that represents our beliefs after seeing our data. Okay, this is called the posterior. Is this okay? So we start by saying, this is what I believe to be true about mu. Okay, it could be something like you could start off with very vague beliefs, right? We could start off by saying, like, you know what, I want to estimate the average height of a student at UCLA. Right? Or like, how tall is the average student at UCLA? And we're like, you know, I have no idea, okay? Because we've got short people, we've got tall people, we've got some really tall athletes and stuff like that. So if we took everybody at UCLA and we measured how tall they are and we get the average height, do we have any idea what it will be? No, we don't, okay? But we do have some vague notion, okay? I can be like very certain, I have very strong beliefs that if we average everybody's height, it will be higher than 4 feet. And if we average everybody's height, it will be lower than 7 feet, right? Okay, that sounds fair, right? But anything between 4 and 7 feet, I feel like, I don't know. Anything in there is technically possible. And I would guess something between 5 and 6 feet is most likely, but I really don't know, okay? So my prior beliefs would be something like, so we would, across, you know, all possibilities, I would have something, you know, fairly low probabilities around 4 and 7, and so I would go 4, 5, 6, 7. I would probably draw something like this, okay? To try to say that, like, I think values around here are most likely, and, you know, so this is like my beliefs about the average height of everyone at UCLA, okay? Then we gather data, and then after seeing our data, so maybe we randomly sample 100 people, and with the 100 people, the average height we got was 5'7", okay? I have no idea, all right? Then our posterior beliefs will be updated with probably 5'7" being something, okay? So maybe our data is 100 people, and X bar is equal to 5'7", okay? And so my posterior beliefs going from 4, 5, 6, 7, you know, is probably going to be something like this, okay? Saying that 5'7", as far as mu goes, mu is very likely to be 5'7" or something a little bit higher, a little bit lower, okay? Very likely to be between, I don't know, 5'6" and 5'8". Okay, but could also be lower or higher than that. Okay, and so now we have an updated beliefs, a distribution to represent what we believe mu to be. Okay, does this kind of shift? Does this make sense? So in the classical view, we said mu was a fixed value, no probabilities associated with it, okay? In Bayesian statistics, we say that mu itself is a random variable drawn from some distribution. And after looking at our data, this is what our distribution looks like. We believe that, you know, mu is drawn from this thing saying where, you know, values like 5'7" is most likely, okay? But technically, it could be higher, it could be lower, things like that. And we just associate, we'll say, you know, the value of being 6 feet, it has a very low probability, okay? And whatnot. So now we have probabilities associated with the resulting mu. Yes?
How do you update your beliefs?
Yeah, I haven't talked about that yet, okay? So the way we're gonna do this is gonna be using Bayes' rule. Was there another question? Yes?
Situations where you're just like, I guess you like don't know at all, but like the distribution could possibly be like you don't want to guess.
Like if you have no context whatsoever?
Yeah, like what you just
Like you're saying like, you know, how much money is there in the world right now, right? And you're just like, I have no idea, right? Or like how many rocks are there? Okay. Okay. We just go, it's a lot. It's a big number. Yeah, you would have to set up your prior distribution to represent like almost anything is possible, right? We can't, you don't want to have a prior distribution that says every value between negative infinity and positive infinity is equally likely. That's not going to be a good one. But you can have like, you can modify something. Maybe like you can modify like an exponential distribution, which technically goes off to positive infinity. Like if you know it's a positive value, you can modify some kind of exponential distribution that technically goes off to positive infinity or something, and things like that. So generally you can figure some kind of distribution that can represent loosely what you might believe. But yeah, you can have a prior distribution that's very, very, very wide, right? Like, I have no idea, right? Like how much water is in the ocean? I don't know. Okay, well, anyway, all right, and so, we're out of time, but let me just say this, okay, so if you remember Bayes' rule, we have the probability of B given A is equal to what? The probability of A given B times the probability of A divided by, I'm sorry, this is wrong. The probability of A given B times the probability of B divided by the probability of A, right? So this is what we have for Bayes' rule, and basically we apply this to this, okay? So we have, what is the probability of our parameter mu given our data? And this is going to become what's the probability of our data given some value mu times what's the probability of mu divided by the probability of our data. Okay, so this is where we're headed. Okay, on Friday we'll talk about the beta distribution, and we'll look at the kind of the beta binomial example of Bayesian statistics, which is kind of the classical intro into this subject. And then we're going to be kind of working with, in the context of Bayesian statistics, we'll be exploring Monte Carlo methods. Okay, so we'll be learning our Monte Carlo methods in this context. Okay, we'll see you guys on Friday, and have a good couple days.